You know, everything around us is changing, all the time. But what if I told you that all that change, from a star exploding to an ice cube melting, could be sorted into just two simple categories? Well, today we're diving deep into the fundamental and fascinating difference between physical and chemical change.
So think about this for a second. You fry an egg in a pan, an ice cube melts on the counter. I mean, both are changing right in front of your eyes, right? But one of them is just a temporary disguise, while the other, that's a permanent transformation, right down at the molecular level. Stick with me, and you'll be able to spot the difference every single time.
So let's start with that great divide. Because really, understanding these two types of change is the key to understanding how pretty much everything in our world works. Okay, first up, we've got physical changes. Now this is all about appearances. It's superficial. You can change the shape, the size, or even the state of matter, like from a solid to a liquid, but the core substance, it stays exactly the same. You haven't changed what it is on a molecular level. Water is just the classic example, isn't it? You can freeze it into solid ice, but it's still H2O. You can boil it into steam, and yep, it's still H2O. The molecules themselves haven't been rearranged into something new. They're just, hanging out differently. Think of it as the same exact substance, just wearing a different outfit. Now, for the other side of things, chemical changes. And this is no simple costume change. Oh no. This is a fundamental identity swap. A chemical change literally rips a substance apart at the seams and reassembles the pieces into something completely new with totally different properties. Maybe it's a new color, a new smell, or maybe it suddenly becomes flammable when it wasn't before. Let's go back to our friend water. If you run electricity through it in a process called electrolysis, you can actually tear those H2O molecules apart. What do you end up with? Hydrogen gas and oxygen gas. You started with water, but you ended with two entirely new substances. That is a chemical change.
So here's the ultimate cheat sheet. It's this simple. For a physical change, just ask yourself, is it still the same stuff? But for a chemical change, the question is, has it become something completely new? Frying an egg? That's chemical. You can't unfry it, right? Melting an ice cube? Well, just pop it back in the freezer. That's a reversible physical change. Easy.
Okay, so if physical changes don't create new stuff, what are they actually good for? Well, it turns out they are fantastic for separating things. Let's see how this works in the real world. Imagine you've mixed alcohol and water together. It looks like one single uniform liquid. How in the world could you possibly separate them without some kind of crazy chemical reaction? Well, the secret is to exploit one of their different physical properties. You do it through a process called distillation. Here's the play-by-play. You heat the mixture up, and because alcohol has a lower boiling point than water, it starts to turn into a gas first. This alcohol vapor then gets funneled through a cool tube, which makes it condense back into a liquid, and you just collect it in a new container. Voila! You're left with pure alcohol and pure water, all separated just by using physical changes. So physical changes are great for taking things apart. But what about building something new from scratch? For that, we need to dive headfirst into the world of chemical reactions.
The language here is actually pretty simple. The ingredients you start with, those are called your reactants. And the new substances you end up with, we call those products. That's it. Every single chemical reaction is just the story of reactants transforming into products. So how does this transformation actually happen? Do the molecules just get a memo and decide to change? Nope. It all starts with a crash. It's something called collision theory, which basically says that for reactants to become products, their individual particles have to physically smash into each other. No collision, no reaction. It's that simple.
But here's the catch. Not every collision works. It can't just be any old fender bender. It has to be a meaningful one. First, the particles need to collide with enough energy to actually break their old bonds. And second, they have to hit each other in the perfect orientation, kind of like two puzzle pieces clicking together. You need both the right amount of force and the right angle for reaction to actually happen. And how important is all this? Well, it's basically the reason life exists on Earth. I mean, look at photosynthesis. A plant takes in super simple reactants, carbon dioxide and water, and using energy from the sun, it creates entirely new products, glucose for its own food and the oxygen we all breathe. This is a chemical reaction on a planetary scale.
Okay, so we know what reactions are and how they happen. The final big question is, can we control them? Can we make them go faster or slower whenever we want? And the answer is a big, resounding yes.
The best way to think about it is like you're in a chemical control room. You've got 4 main dials that you can turn up or down to either speed up or slow down a chemical reaction. Let's take a look at each one.
Each of these dials basically works by changing how many successful collisions happen. You crank up the temperature dial and particles start zipping around faster, leading to more frequent and more powerful collisions. That's why putting food in the fridge slows down spoilage. Or you can increase the concentration, packing more particles into the same space, making collisions way more likely. Increasing surface area, like when you grind up meat, exposes more particles to the outside world so they can react faster. And finally, catalysts, like the enzymes in your laundry detergent, act like little chemical matchmakers, helping collisions happen way more easily and efficiently.
And really, this is the whole point. This isn't just some abstract science lesson from a textbook. As the slide says, understanding this difference is truly fundamental. It governs how we cook our food, how we build our cities, and even how we develop life-saving medicines.
You know, from the coffee you brew in the morning to the battery powering your phone, you are surrounded by, and you are constantly causing, both physical and chemical changes. You're already a master of matter in your own daily life. So the only question left is, what will you choose to understand and to change next?